know, just how you feel.
True.
Okay. So how is the test?
Good, straightforward.
Okay.
I missed the lead.
To be honest, I mean, I like the fact that it was all on iLearn as well, so it makes it easy and everything. But since they're the exact same questions, all they're doing is doing everything in copy paste. And
Yeah,
it kind
what
of.
it does is it makes it so that my grading time is cut down by about 75%.
Oh, I understand. It just,
It doesn't help you at all.
at the time I'm sitting there going through it going, this is so unnecessary and annoying.
Well,
but-
it's unnecessary for you.
Yes.
But it's necessary for me.
See, I understand.
more work because it saves me about 6 hours.
See, I understand that. It's just
Wow, 6 hours.
kind of blew my mind.
Okay.
Are you sure? Can I actually email it to you?
Yeah, go ahead and email it to me. That would be good.
Okay.
Yeah, that'd be good. Okay. All right. So, yes, I understand that's annoying. I'm well aware. So.
I thought it was just fine. When I actually end up emailing, or not emailing, when I copy and paste it in, or when I have to input the number in there, I'm kind of like second guessing myself sometimes. But I mean, I see like this big box like, hey, I'm typing this explanation, and I have like 3 sentences. I'm like, oh, that box still looks pretty empty. Maybe I should type more.
Yeah, I don't get to choose box size. It's a default.
No, I know.
Sometimes it's like put in one number. And
But the whole copy and pasting doesn't take too long. The one part I was surprised about is it doesn't allow you to copy and paste in, like just your numbers on those small text boxes when you're looking for the exact number. It doesn't allow you to copy and paste
Oh,
them.
really?
But that's no big deal. I mean, it's a couple numbers, but anyway.
yes.
So I found it, but it's not the completed one.
Okay, well, so hand me what you have, okay? Because I think for a lot of it, if it's in iLearn, you'll be mostly okay.
Just don't have any of my graphs or anything.
Does it have any graphs in it?
No.
Keep looking. I'll help you look after class if you have a minute. I don't know what I'm doing. So we'll just wait for this to show up. And this is a test you guys have all seen before. Did anybody get the reading done? Is everybody going, ha ha, we had a test, we didn't read anything?
Yeah.
Okay, so you've done this test before. You actually covered this in 220X.
Exactly.
You guys are doing it. Sorry. Try to start. Okay. Alright. So this is the same test you guys did in 222. So the last chi-square test you did, that was one you had not covered in 220X, but this is one you have covered. I wanted to show you how to do it in R because dealing with two-way tables and more complex and pie charts and bar charts would be helpful. Today we're going to cover the basics of the chi-square test, how to actually do the test, looking for the requirements, and then Wednesday we're going to spend dealing with the relationships. Because remember with ANOVA, when you run it, that you can't say what's different, just that something is different?
Yes.
Okay, good. Like, are you there?
Yeah.
So it's a similar thing with chi-square. It can tell you if they're independent or if they're not independent, but it does not tell you the nature of the relationship. So today we're going to talk about the test. Wednesday we're going to look at methods for assessing a relationship that is or isn't there. So Wednesday is actually a far more involved day than today is. So beware. So first of all, with chi-square test of independence, one thing you have to understand is what it actually means to be independent. And the actual definition of independence, this is a probability idea, so this is an actual mathematical definition, is that the occurrence of one event does not affect the probability of the occurrence of the other. So in English, what does that mean?
Boom.
Oh, that's the name of the
That one event doesn't make the other one happen or not happen.
Okay, so that's part of it.
If it doesn't affect the probability of the occurrence of the other, then they are completely independent, which means that if you were to use regression, their correlation wouldn't even be like 0.1.
It would be 0.
Really, it would be 0. That's what I'm saying. Is it wouldn't even be like 0.0001.
Oh, yeah.
It would be 0.
If they were perfectly independent.
Yeah, if they were
yes.
perfectly independent. Yeah.
Yes, yes. So, yeah, so basically, like, what would be some examples, an example of some events that are independent?
A rooster crowing and the sun coming up.
Also have
Actually, they
roosters.
know they do crow when the sun comes up, so those are not independent.
I thought they just crow all the time.
They actually close the sentence.
One next month.
Hey, whether or not lightning strikes and I tie my shoes.
What's that?
Say, two events that are completely independent are whether or not lightning strikes and whether or not I tie my shoes.
Okay, right, okay.
Where are they?
Unless you're more likely to tie shoes. So, other things, one that people don't like to think is independent, but it is independent, is like gender of children or genetic defects. For instance, if you have one child who was born with a genetic defect, it should not influence the chance of the second one having a genetic defect. If you already knew you were a carrier for that. If you have 4 boys, or you could be like my in-laws. Okay, they have 3 boys in a row. What's the likelihood that they have a girl?
50-50.
Okay, 50-50. Then they had a girl, and then they had, let me see, how many? 6 more boys in a row. What's the likelihood of having a girl? 50-50.
How many kids do they have?
12.
Oh.
And 10 of them are boys. So,
Has he renamed himself Israel?
but you should have. Actually, it's funny, my father-in-law is from Sweden, and in Sweden it's like obscene to have more than 2 children, so he just kind of gave up after 4, and he's like, whatever. So, it's kind of funny. So I ended up with 12 kids. So,
Does he know he couldn't?
my in-laws are funny. They're funny. They're awesome, and I love their large family, but they're funny. Anyways, he decided he didn't really have a say in the matter after a while. So, anyway, so those are events that might be independent. But, so what we're going to do with the chi-square test of independence, so this should all be a review. The null is that they are independent, that you have a row variable and a column variable that you put in a two-way table. And we assume that they have nothing at all to do with each other, that what happens in one has absolutely no bearing on what happens in the other, that knowing something happened in one of those row variables doesn't affect or influence the likelihood of something happening in the column variable. For instance, never mind, I'll come up with that. We'll just go along with this stuff. Okay, the degrees of freedom is you have, I'll show you the tables in a minute, but you have a number of rows and you have a number of columns, and you just subtract 1 from each and multiply those together to get the degrees of freedom. And the expected values, I need to get a table. Okay. So just based on the degree, okay, so here we have a situation where we looked at smoking frequency in college students versus how often they exercise. So what would be the null hypothesis?
No effect.
Yeah, that knowing
Smoking and
how-
exercise has no relation.
Yeah, that they're completely independent, which basically means that no, this is the null hypothesis. So we're going to find out if that's true or not. But the null hypothesis is that they're independent, meaning that if you know if someone's a heavy smoker, it doesn't have any bearing on how often they exercise. Like, they're just completely independent. Now, how many degrees of freedom would we have in this table?
6.
4.
9.
4. Okay, so we have how many columns?
2.
3. No. Ignore the totals. How many rows?
4.
4. So what's our degrees of freedom?
6.
6. 2 times, yeah. Now to get the, remember we, yes, go ahead, sorry.
I was just, the quiz that we took last time said degrees of freedom. That's something separate?
Yeah, so this is a different chi-square test. So that one, as goodness to fit, you have like 1 row of data. This
Okay.
one, we have this 2 by 2 table. So the structure's a little different. The chi-square formula stays the same, but degrees of freedom will be a little bit different. And
Is this like two-way or two-way and over?
it's kind of like 2-way ANOVA for categorical data, kind of. Kind of. In a very loose sense.
Okay.
The closest thing we have to relate to it.
Sorry, just because I just did the test and I'm thinking about it, like, well, it's like,
Okay, so remember last time we had expected counts? Yes. Like how many M&Ms we expect to see in the bag, things like that. We have expected counts here, and the way you calculate them, so this is way back on the other slide. I thought it would be more helpful to talk about it with an actual table in front of you. But if I want the expected count for this cell, I take this total times this total, the ones that match it, and divide it by the grand number. And I can do that for each cell. So that's where the expected counts are coming from. So each cell will have its own expected counts. Now, as a quick review, what are the expected counts? They're similar in concept to what we had on Friday.
So it's the count that would be there if the null hypothesis is true.
Right, yeah, so it's what we would expect to see if what was the case.
There was no relationship.
Yeah, if there was no relationship between smoking and how often you exercise, that the expected count would express what we would expect to see in that cell if it was the same. Now, if there was no relationship. Now, they are going to be different in every cell. For one thing, you'll notice that in the study, what groups were the most prevalent? Yeah, never smoked was, we had far more people who didn't smoke. What about in the exercise? Okay, frequently was the most common. So these are actually going to be different in every single cell because they need to reflect the proportions of who we talk to in our study. So we're going to get a much bigger number here for an expected count than we will here because of the proportions in the study. Okay. So where do the observed counts come from?
From our study?
Yeah, they came from the data. So they're on here. That's what's here. Okay, so this is basically what we just went through. The requirements or the assumptions is that all of the expected cell counts are greater than 5. Or, now, I put this down here right before class because I decided to start looking up the actual requirements because most commonly I see that 80% or more of the expected counts have to be bigger than 5 and then you're okay. But your book actually uses a different criteria. Your book says if all the expected counts average to be bigger than 5, you're okay. So I was thinking, well, that's kind of a big contradiction. I mean, it really puts it in a completely different situation. So then I pulled out my old mathematical stats book and it had a completely different requirement. So the one that I see voiced most often is this one with the 80%. But because your book uses the average, I'm going to have you guys use this one, but be aware this is the one that's most commonly stated. But like I said, it's different than the one I had in my mathematics stats book too.
What did your math stats book say?
It said if you take the total number divided by the number of rows and the total number divided by the number of columns, and those are both bigger than 5, you're okay. Which is actually much easier to meet than either of those. So, and it kind of seemed like nobody had a really good mathematical justification. It's kind of like everyone presented it as, you should be okay if this happens. So, I'm not exactly sure where these requirements came from.
Yeah.
But we'll try the one in black for our class. So, but yeah, when I looked online, the most commonly one that was stated was the one in blue, which is the one you learned in 220X. So it just seemed like that was over and over again. However, they almost all quoted the same source for that one, which was the book we used to use for 221. Okay. Okay, so there's our requirements. Okay, so we're going to do the smoking and exercise. So this study was done on college students. Do you think that's important to know?
Yes.
Yeah, it actually has a huge impact on how you interpret the results of this. So we have 4 smoking categories. Heavy, regularly, they are heavy smokers, regular smokers, occasional, or never smoke. And then we have exercise, which is frequently, some, or none. So here's the table we were just looking at. So which categories have the least representation?
Never heavy and never regular.
Yeah, so people who never exercise and are heavy smokers and regular smokers, we only have one person in each of those categories. And who is the most widely represented?
Never.
Yeah, people who never smoke but exercise frequently or occasionally. Okay, so our null alternative is that smoking and the frequency of exercise are independent, and the alternative is that they are not independent. And we have 6 degrees of freedom, which we decided a few minutes ago. So if I were to just, tell you about this setup, I just want to see what you guys think would be the case.
They are.
How many of you think they're independent? How many of you think they're not independent? Okay. So
I
what
didn't
happens?
go, sorry. If they're college kids, I think they would be independent. But I think with regular people, it would be the other way around.
I think I agree with that.
We'll see what happens. Okay, so this is how we're going to put it in R. So getting the data in R is going to be a little different. You're going to have to make a table. It looks like the contingency table. Now, when you guys did this, for those of you who had SPSS or who used Excel from 220X, this is going to look more like what you did in Excel. But for SPSS, this is a completely different setup. You actually, in R, want it to look like the table that we just had on our screen. So you're going to make a matrix, I mean not a matrix, a vector for heavy smokers, one for people who regularly smoke, occasionally smoke, and never smoke. And then I'm going to combine them into a matrix using this function rbind. So rbind takes all those vectors and just smashes them on top of each other and makes a matrix. So each one of those vectors becomes a row in the matrix. Does that make sense? There's also one called cbind, which would make it so it would make them all columns and smash them together in a matrix. So we're going to use rbind, but you could actually use cbind and put them that way too, and then they would be rotated 90 degrees.
Would we get the same results?
You would get the same test statistics, yes, and degrees of freedom. Your table would be rotated 90, but all the numbers would be the same. Okay, so we're going to take, oops, let's do that. So rbind and cbind are really nice, just look up my previous work. They're really nice functions. So basically when I ran heavy, it looks, I get a vector that just has that first row of data. And when I smash them all together in smoking, so you can see it actually maintained the names of the rows, and there is a way, I'm going to show you how to do this on Wednesday, to actually name the columns also. We're not going to worry about that today, but we will worry about that on Wednesday. But as you can see, this matches the observed counts within the 2x2 table that we just had. Okay, so there we go. That's what we just did. Now you can use the chi-square test. It's the same function that we used last time. If you give it a vector, it does a goodness of fit test. If you give it a matrix, it does an independence test. So R knows what you want just by the formation of the data that you put in it. So same command you used last time, it knows what to do. So when you put it in, you get this output, and the chi-square statistic is 5.4885, and we get a p-value of 0.4828. So what's the verdict?
Failed to reject.
So we failed to reject, which means,
They're independent.
yeah, we can't conclude they're not independent, so we're in the world of double negatives. So basically, our evidence doesn't really show that there seems to be much of a, these groups, they don't really seem to have anything to do with each other. So this is where I think the college thing comes into play, huge, is because I think if you went outside of college students, you'd probably see a very different relationship. But in college students, it does seem to be that they're not related, at least according to this study. We want to know more about this study.
I think too, it sounds like a really subjective test, like, yeah, I go frequently, like, what is frequently,
Yeah, you notice there was no definition as to what's frequently, and I don't know, maybe when they conducted the study, there was a good definition, but a lot of times there isn't. A lot of times they're just like frequently, occasionally, and it's like, frequently, I never smoke. I don't smoke every once in a while.
I've just been seeing the last one.
If I could explain this question, right? Does the test tell us if, for example, the difference between the group, there is a relationship, and can we tell the difference between if like really heavy smokers go to the gym all the time or really heavy smokers never go to the gym? So we can't really tell the difference between them, right?
Nope, see, if we've gotten significance, we would just know that if I knew something about the category they were in for smoking, I would know something, would alter the probability of what group they were in for exercise frequency. But as far as in what way, it doesn't tell us that. So that's what we're going to focus on
I'm glad you
Wednesday.
understood what I was trying to say.
Did that make sense?
Oh yeah,
Is that your question?
Yeah,
Okay,
that's right.
good. Yeah, so, but right here we're just saying that we don't know, and this is where I think the college student thing is super important. So we failed to reject the null, and they are okay. So we basically would say they don't really have anything to do with each other, according to this study. So we're going to look at the requirements. So we talked about the requirements. Do you guys remember what they were?
80% greater than 5, average is greater than 5.
Right, okay, so the first thing you just look for is, are they all bigger than 5? Because that's the easiest thing to check. Are they all bigger than 5?
No.
Okay, so then we have to go to step 2, which is the 80% or do the average. So, did you notice how I got the expected counts in the first place? Yeah, when I ran my chi-square test back here, I named
My
it.
intuition tells me that.
Yeah. Okay. Let's see, where did I put it? So you'll notice back here, I actually named my chi-square test. So if all I want is chi-square and degrees of freedom, I don't need to name it, it'll spit it out. But remember with like regression and ANOVA, there's all these pieces embedded in that test. So if I name my test, I can get to those. So I decided to name it smoking test because then I can get to things like the expected counts. There's actually a lot of stuff embedded in that test that we can get to. Yes, sir?
If you wouldn't have named it, would you use chi-square.test?
Yeah, so you could use chi-square.test and then $ expected, and then all you would see is the expected
Okay.
values. It wouldn't spit out the actual test for you.
Okay.
Oh.
Yeah.
So
So
it'd be like the one where you have a
yeah, so like I can show you how it would work out. So if I did, just to make sure. Thank you. Okay, so if I type that in, I just get the expected values, but I don't get to see the text. And then if I take this off and run it, I see just the text. So you can actually, if you just want pieces, you can always put a $ and just grab the piece. But I like, if I know I want multiple pieces, I always name the whole test and then I can just grab them off as I want them. So, does that make sense? All right, so, okay, so we have 4 of them. So do we, okay, so if we use the 80% criteria, do we meet the requirements?
No.
Definitely not. But if we use the mean requirement, and you can actually, okay, so we fail the first wave. Oh, and everything does have to be bigger than 1. If you have any expected counts that are less than 1, you're toast right off the bat. But you can actually take the mean of the expected values. So it's interesting, you know, even though those are all in a matrix, if I use the mean command, R will take the average of everything in that matrix. So we can see that the average expected count is 19.66. That's right.
So by toast, does that mean you should stop running this
It means
test?
your test is unreliable.
Okay.
Yes. So everything's now off kilter and your p-value isn't reliable and all of that stuff.
So the expected values are coming from the observed values, right?
They're, yes and no.
Because that doesn't.
Well, see, what it is in my study, I had so many people that smoked, and I had so many people that exercised frequently. And when I have all those counts of the demographics, I can figure out how many should be in that category combination if there really is no relationship. So I need to know how many are in each category in my study to get those numbers. But I'm not actually using how many were in that category to get it. Does that make sense? No? I can tell you're like,
It's okay, you can keep going, I'll probably figure it out.
Let's see if we can mull it over a bit and we'll come back to it. It's not any, it's, yeah, that used to throw me off too. I was like, aren't I just using my data to?
Yeah, because I'm like, well, that's observed, so always going to skew your expected. But
It's basically saying if I have a study, if I do a study that has 87 heavy smokers and 120 non-smokers and 52 people who exercise heavily and whatever the other amount would be for those who don't, you know, how would I expect those to be divvied up if there really was no relationship? If I really was just randomly
Oh, so you're saying
drawing-
you're like kind of separating the variables, like you're separating that, and
Right.
and then using that as your expected. Okay, that makes
Because
sense.
if I have a
Actually,
study
that
where
makes sense.
85% of the people didn't smoke, well, I would expect a lot more people to be in those categories even if there's no relationship.
So you're
It
just
has to
getting the
reflect that.
percentage from the separate variables.
Right.
Okay, that totally makes sense. Yeah.
Did I see a hand over here?
So this, what you just did here with this mean for smoking test expected, that's actually for the whole grid itself, that's not for like the rows.
Yes, I took all 12 of these numbers. Well, okay, R took all 12 of these numbers, added them up and divided by 12. So by one criteria we fail, by another criteria we meet it. I have not been able to track down good information on what is the better criteria. Good question, Brian?
Kind of.
Well, never mind. I mean, I was trying to think how to calculate that without R, but that, I'm not sure if it even matters.
You mean the mean?
No, the expected values.
Oh,
Because
yeah.
they're really just like percentages multiplied. So
Well,
that
remember,
they're
it's the row total times the column total divided by n.
Right, okay.
So and you just do that across the grid and you get them all. So it's a really easy calculation.
So as long as we pass one of the requirements, we're fine. As long as nothing's below one.
Well, no, they,
Black one, right?
no, if anything's below 1, you're
Yeah, it's dead.
toast. But that's not enough. I mean, if I have a whole bunch of expected
Yeah, but
counts between
as
1
long
and
as
2, I
everything's,
do not
as long as
finish it.
everything's over 1, but 80% of it is not under 5, well, 80% of it's not over 5, but the average, the mean is over 5, then we're fine.
Well, that's why I was saying, like, I haven't been able to track down good information about which of these works better. Or
Okay.
even where they came from, to be honest with you. So that's why I opened up my mathematical statistics book, because usually it's like, there's some great mathematical explanation as to why it has to be so, and there wasn't one. It was just like, it's a good idea if this is the case. I'm like, great. But anyway, so my guess is it came from experience, and so the rules, do you have more insight, Dr. Cromar, on that?
Not really. I mean, it's. No, I thought maybe I might add something, but.
A lot of times they're done through simulation, like just repeating the process
Right.
over and over again, and finding out where they break down, which is why you sometimes find multiple guidelines. But as far as which one works better, I'm not really sure. The most stringent seems to be the 80%, which is probably why I see it the most often. So we fail one, but we meet the other. For this class, we're going to use the average just because that's consistent with your book.
There we go.
So what happens if all the requirements are failed?
Then you shouldn't be doing a chi-square test. Your
You should
P's,
take another model.
yeah, you got to start looking. Well, yeah, basically your p-values become very unreliable.
Every other time anyway.
I was going to say that with many different types of tests, when you're trying to, whether it's detecting differences or meeting requirements, I mean, there's some liberal, not political sense, but but when we're mathematical sense, there's some that it's okay, you can be really loose about it, that makes sense, and others not so much. I guess it probably depends on what you're seeing probably is a small sample of what you see throughout the statistics stuff, if you will, where people just have different attitudes about should we be liberal or conservative on this, if that makes sense.
Right, yeah, and where I'm seeing so many different ones, and the 80% does seem to be the most conservative one.
Right.
I can guess that a lot of people stick with that. But like I said, I've seen a few. The most liberal one was the most one I found on my mathematical stats book. I was surprised at how liberal that one was. But we'll do the mean just because that way when you go back and read your book, it'll be consistent with your book. So, okay, so did that make sense? Seem okay in R? These aren't too tough to do in R. Okay, the next one we're going to do is a 2x2 table. Okay, so we have a city. This is probably made up Day12. So I just found this somewhere in a book.
What do you see?
I stole their data.
That's funny.
So a city did a study. What?
It was just funny that you thought it was made up.
Okay, yeah, I think it is. N equals 10,000 is always suspicious. So they looked at gender and voting, and so you probably shouldn't draw any concrete real-life conclusions from this data. It'll get the point across from a chi-square perspective.
I already believe it.
So, oh wait, let me go back here. So what's our null?
Voted and gender are requiring.
Right, so your gender and the likelihood of voting are independent, meaning that neither gender is more likely to vote than the other. What would be the alternative?
That gender does have an effect on the vote?
Or that they're
Likelihood
non-independent?
of voting and gender are not.
Yeah, so that would be something like if I know somebody's female, then I know they're more likely to vote or less likely to vote. Okay, so degrees of freedom. It's easy on this one, it's 1. And this is how we're going to set it up, just like we did before. Okay, so just make a vector for each row, and then you're going to use R-bind to squish them together, and you're going to get your data table. And then when you do a 2x2 table, you have to do something in R that you don't have to do with any other one. Whenever you're doing a 2x2, you need to add in this correct equals false, or you will get the wrong answer. And I'm not quite sure why, but it performs the calculation differently for a 2x2 than for the others. So just make sure you get that extra statement in there. That's why I put in a 2x2 example. But this only goes in there if you're doing a 2x2. So if you look back at the other one, it was not in there. So what do we find out?
That you reject so that they are not independent.
Right. So what does that mean in a real life sense?
That
Really.
gender will does have an effect on likelihood of voting.
Yeah, so basically if I know somebody's gender, then I know if they're a little more likely to vote or a little less likely to vote. Or if I know somebody voted, I don't know. You know what I'm saying? Okay, so basically what you guys just said, so yes. Okay, so we have our expected counts, and are we okay?
I think so.
Yeah, they're gigantic. And with this much data, you're going to be just fine. Okay, so results that we have a small p-value, so we reject, and so we can conclude that they're not independent. And a couple things you need to note about chi-square is that it will tell you if they're independent or dependent, not independent, but they will not tell you the details of the relationship. So at this point, do we know who is more likely to vote? Okay, we don't. It just tells us somebody's more likely to vote. And the variables must be mutually exclusive. So what I mean, you guys remember this? Like, what does the word mutually exclusive mean? You don't have to read my definition off because it won't quite be.
It means they don't overlap in any way.
Yeah. So basically, if I have a person in the female voting category, can she be in another category? No. So you need to be careful about that. Sometimes people have, when they run a test, they accidentally will put the same person in multiple categories without realizing that's bad. So you have to be careful about making sure that everybody in the cells, that those are all completely different people, that you don't have two people in the same cell. Also, don't exclude part of your data set. So make sure if you have the variables, for instance, if we had a, I don't know what our third voting variable status would be, but in this case, if we had one, it shouldn't be removed from your data set. Because if it was part of your study, it should be in with your chi-square. It would affect the balance of everything else if you don't put it in. Okay, now this is what we're going to hit on Wednesday. We don't know the nature of the relationship, so what you're going to do is you use pie charts and bar graphs and row and column percents to help you figure out the nature of the relationship, because chi-square won't tell you that. Oh, that's actually part of next time. Okay, so go ahead and you get to run the chi-square test on a couple of data sets. The first one has to do with handedness and gender. This is a real data set. The Haynes data set, the Haynes study is run out of I think it's run out of CDC or NIH. And they test all kinds of interesting things, including apparently if you're right-handed, left-handed, or ambidextrous. So. And then number two, and it's funny because I put this together last semester and there was an extradition issue going on, and there happens to be one going on right now, but I actually did not choose it because of that. So it has to do with extradition treaties with Northern Ireland and religious persecution. So Protestants or Catholics more likely to get convicted for terrorist crimes, basically, is the question.
It was.
This is in 1991, and yeah, it was massive. It was huge. Yeah, there was like lots of bombings and terrorist activity in Northern Ireland until fairly recently, actually. Wow. So, yeah. So,
I need your help with something.
okay.